for this Thar talk. I heard him in one of the Nature portfolio web workshop, and there he spoke about some other topic. When I invited him, he accepted this invitation, and then we discussed uh, what should he speak on. So he offered two topics, one which was same as he spoke in the Nature talk, and another one was this. So I got greedy. I wanted to hear a different talk. So I told him, let's talk about soft electronics and microfluidic systems for the skin this time. And maybe I can persuade you to join us again after a few months and give the talk that you gave earlier. So Professor John Rogers obtained his BA and BS degrees in chemistry and in physics from the University of Texas, Austin in 1989. And then from MIT, he received SM, which is master degrees in physics and in chemistry in 1992. So his passion for physics and chemistry comes together for his PhD degree in physical chemistry in 1995. And for 2 years, then he was a junior fellow in the Harvard University Society of Fellows, after which he joined Bell Laboratories as a member of the technical staff in the condensed matter physics research department, where he served as a director from 2000 to 2002. Subsequently, he spent 13 years as faculty in University of Illinois, most recently as Swanton Chair Professor and Director of the Science Material Research Laboratory. He just now told me that he was in Urbana-Champaign campus of University of Illinois. After that, he moved to Chicago. We're just discussing one of my favorite cities in the United States, where he joined Northwestern University as the Louis Simpson and Kimberly Querrey Professor of Material Science and Engineering, Biomedical Engineering and Medicine, with affiliated appointment in Mechanical Engineering, Electrical and Computer Engineering and Chemistry, and is also the director of recently endowed Querrey Simpson Institute for Bioelectronics. He has over 80 patents and patent applications, more than 50 of which are licensed or in active use by large companies or the startups, some of which he has co-founded. He's got many awards. Most notable is the MacArthur Fellowship in 2009, which is known as the Genius Award, Lemonson MIT Prize, National Security Science and Engineering Faculty Fellowship, Smithsonian Award for American Ingenuity in Physical Sciences, MRS Medal, the Benjamin Franklin Medal from the Franklin Institute, and the Guggenheim Fellowship, which is we received earlier this year. He is a member of National Academy of Engineering, the National Academy of Sciences, the National Academy of Medicine, the National Academy of Inventors, and AAAS, that's the American Academy of Arts and Sciences. We're really proud to have him as a speaker in the Thar Talk series, where he will talk about soft electronic and microfluidic system for the skin, which he gave a subtitle as Soft Skinned Interface Variable Technology for Health Monitoring. Over to you, Professor Rogers.
Okay, great. Thank you very much for that kind introduction, and thank you for the invitation to come here and share with this group some of the research that we've been doing in my team over the last period of time. So let me see if I can share my screen. Let's see, here we go. So hopefully you can see that title slide. So I have decided to kind of talk about some of the things that we've been doing in soft skin interfaced wearable technologies. So these are health monitoring devices that interface with the skin at relevant anatomical locations to capture clinical grade streams of data that can be interpreted and processed to develop deep insights into physiological status. And I selected this topic because there's a strong component of data science. And it's an area where I think there are tremendous opportunities for machine learning and artificial intelligence to be brought to bear on these complex but highly information-rich data streams, so that insights can be extracted from them to help care for patients, to improve patient outcomes, and to do that in a way that is cost effective as well. And so we're thinking in terms of continuous monitoring outside of a hospital setting. So the consequences that there is a tremendous amount of data that needs to be processed and interpreted in an intelligent way. And I think machine learning and convolutional neural networks and so on will play a very prominent role in this space. Now, I'm a hardware person. I'm not a data scientist. We do a little bit of that in my group out of necessity, but I think the audience here, likely has much deeper expertise than we do in machine learning. And so I'm excited to share some of these advances in hardware with this audience, because I think their engagement or engagement of the data science community will be extremely important in realizing the full benefits of the kind of technology that I'll share with you today. So the idea is just to give you a sense of where things are headed in terms of measurement capabilities relevant to health monitoring, with the hope that it will pique your interest and lead to your activities and maybe launching efforts in these kinds of areas, because data science is, as I mentioned, so critically important. So my home department is material science and engineering. As you'll see, a lot of the technologies that we develop, though, require expertise across various other areas of engineering science, including electrical and computer engineering, biomedical engineering, mechanical engineering, so on. So most of the students in my group, span these multiple departments, and I have affiliations there. As well, I have an appointment in the medical school because, as you'll see, developing the hardware in close collaboration with the medical community is really essential for making meaningful progress in these directions, to understand what kinds of measurements need to be made, to engage with a patient population so that the engineering can be refined to address real world requirements for meaningful use. And so we're deeply embedded in the medical community here in Chicago. And as I'll mention, throughout this talk, we've deployed far beyond Chicago, really around the world. And so that's an important part of our work as well. So I'll start with a little bit of a background and an overall motivation for our work in this area, and then I'll describe two hardware platforms that are reaching high levels of technical maturity, so far beyond the level of academic curiosities, to devices that are now manufacturable at scale and deployed, as I mentioned before, at a global level. And the first of those platforms involves wireless digital electronics for measuring biophysical signatures of health status, which we refer to as epidermal electronics because of their skin-like construction. I'll step you through the details there, but not with a tremendous emphasis on the underlying material science and the hardware, but really sort of trying to highlight the kinds of data streams that can be captured, again, to try to kind of pique your interest in how those data streams can be best interpreted and analyzed using machine learning approaches. Then the second device platform is one that addresses important requirements in biochemical measurements of health status. So these, as with these epidermal electronics, are skin interfaced, but instead of digital sensors, we have embedded microfluidic capabilities into these devices for capturing very small volumes of sweat as it emerges from the surface of the skin, and then for doing in situ analysis of concentrations of key biomarkers of health status. So that's the overview. I'll go ahead and then jump into this. I think I have maybe about 45 minutes of content, and then hopefully we'll have a chance to discuss implications and for me to answer any questions that you may have. So at a high level, what we're attempting to do is to develop microsystems technologies that are biocompatible in the sense that they can be integrated with soft tissues of the human body for long periods of time to establish intimate interfaces to biology for monitoring biological processes. Again, those that are relevant to health status, not only at a specific time, but also health status in the sense of a predictive trajectory of how health is likely to evolve over time into the future. So really thinking in terms of microsystems technologies, pretty much everything that you could imagine: electronics, optoelectronics, microelectromechanical systems, photonic systems, microfluidic technologies, all of which are very well developed. But in physical formats that don't support integration with biology very effectively. So a silicon integrated circuit, for example, is a very sophisticated, well-developed piece of technology, but it exists only in planar, rigid physical form factors, which are highly mismatched from the soft, curvilinear, time dynamic surfaces of the human body, the brain, for example, where you might want to use electronics to interrogate electrical processes of the brain, or maybe stimulate neural processes in a way that could address various disorders of the brain. But doing that with a silicon-based IC as it exists in consumer electronics technology, is not addressing the kinds of requirements you'd have to satisfy for integrating with the brain. So we'd like to make electronics, optoelectronics, and so on look more like biology from the standpoint of mechanical properties, geometry, and you'd also need to construct those devices out of materials that themselves are biocompatible. So that's what we're trying to do. You can think about those kinds of systems in the context of the brain, but many other vital organs could potentially benefit from the integration of electronic, optoelectronic, and so on functionality. So the heart is another place that we've been interested in electrical activity. The heart is an electromechanical system. If you could monitor electrical behavior of contracting cardiomyocytes, perhaps you could stimulate the heart in a way that would eliminate arrhythmias before they develop, for example. But other places too, the spinal cord, the peripheral nerves, the kidney, the bladder, the lung, the diaphragm, all different points of integration that we've explored. What I'll talk about today is one representative organ that is very attractive because, unlike the heart and the brain, you can integrate with this organ system in a way that exposes the patient to minimal risk, and that is the skin, the largest organ of the human body, where soft electronics could be delivered to the surface of the skin to establish an intimate contact where the skin could be used as a measurement interface, a measurement window for capturing characteristics of underlying body processes. So that's kind of a high level description of what we're trying to do. And accomplishing those goals is an interdisciplinary engineering effort around material science, electrical engineering, hardware, essentially. But as I mentioned before, the data streams represent the outcome of successful efforts of that type. And then the question is, what do you do with the data? So again, just to reemphasize, what we would like to do is reformulate this kind of technology, the silicon integrated circuit, into a platform that looks more like biology from the standpoint of geometry and mechanics. So current silicon integrated circuits have mechanical properties dominated by the underlying silicon wafer, and they have geometries also defined by the planar layout of the wafer. And so, the question is, how do you move beyond that set of physical properties to something that could, softly, integrate with a curved surface? And you can either do that by moving to novel materials, electronic materials, carbon nanotubes, maybe graphene, maybe 2D materials, organic polymer, semiconductor systems, and so on. That would be one way. The other way to do it would be to think about novel ways to deploy silicon and other well-established inorganic materials to combine them in a hybrid fashion with organic polymers and elastomers and so on to achieve, um, you know, physical properties that are compatible with biology. And it's really that second strategy, that hybrid heterogeneous kind of material strategy that has worked best for us. And so because this is not meant to be a talk around the underlying physical science associated with these technologies, I'm just going to skip to the end and just make the statement that you can in fact do what I just said, that you can take silicon, you can take silicon dioxide, you can take copper and so on, and distribute those materials in integrated circuits that when embedded in soft elastomeric polymer matrices, adopt the physical properties of, let's say, the skin. And you can do that by paying attention not only to circuit design to support the kind of function you're hoping to achieve, but also from the standpoint of mechanics design, where you think about the geometries and the layouts of the circuits from the standpoint of the mechanical properties at the system level. And so we do, through collaborations that we have here at Northwestern, quite a bit of computational modeling of how these entire systems deform and stretch and twist, as they're integrated with the surfaces of the skin, with an eye toward achieving effective mechanical properties that are comparable to the soft tissue at the point of integration. And so you can think about these as hard, soft, hybrid composite material systems, where the function is important not only from the circuit design standpoint, but also from the standpoint of mechanical properties. And so turns out you can do that. You can create wavy structures that move like accordion bellows and buckle and twist in ways that minimize the mechanical load associated with the intrinsic material properties, but still embed those high modulus materials in an overall construct that has an effective low stiffness and high degree of mechanical compliance. So we have been thinking about those kinds of strategies for a number of years. I think we felt like we were pretty comfortable with those concepts and with how they could be implemented in a realistic way. Published those ideas in 2011, and that's kind of what's illustrated here on this slide as basically a demonstration platform with those characteristic features. And as you can see, you end up with a device that is very much like skin itself. And so these are platforms that can integrate with the surface of the skin in a way that's almost physically imperceptible. So and that's a key feature. They can be positioned at any location across the body, and then once they're laminated on the surface of the skin, the subject or the user of the technology has no perception that the device is in fact bonded to their skin. So it becomes imperceptible. It becomes something that is burden-free from the standpoint of any kind of constraint on natural daily activities. So that was 2011. We got a little bit better at this in 2014 or so, published another paper. And then from that point on, I think a major, stream of work in the group is to understand how these technologies could be designed to address real clinical needs, real patient populations, and sort of requirements to address specific conditions and in specific environments with a full consideration of the cost as well as the function. And so that's kind of what we've been working on, and I'll bring you up to speed on the latest versions of that kind of technology and the sorts of data streams that we're collecting in a second. But before I do that, I would just emphasize again, these devices are mounted on the skin not for the purpose of convenience. That's part of it. But the main goal is to establish a low impedance measurement interface to underlying body processes with the skin as the window for making those measurements. And so you think about conformal contact between the devices and the skin is an important consideration, not only from the standpoint of adhesion, but from the standpoint of impedance of the measurements that you're interested in making, whether they're thermal or optical or electrical or so on. So these kinds of serpentine type layouts not only give you this favorable sort of low modulus mechanics, but it also gives you geometric conformality against the textured natural surfaces of the skin, which is what you're seeing here. This is a magnified colorized scanning electron micrograph of this kind of mesh type architecture that we find to be very useful for these systems, in contact with that textured surface of the skin. So it's a polymer replica of human skin with one of these devices laminated on top. So that's kind of what it looks like. Now that skin contact now immediately allows you to make all sorts of measurements that are currently confined to a hospital or laboratory setting. So these are measurements that cannot be made effectively with a conventional wearable like an Apple Watch because of the lack of that persistent skin interface. The watch itself rattles around on the wrist, and you can do certain types of measurements when you don't have that physical contact with the skin. But there are some essential measurements that really require that contact. And electrocardiograms would be one example here illustrated on the left. So you can take these kinds of mesh type electronic tattoos essentially, and you can laminate them on the surface of the chest. And when you do that, you can actually pick up electrical activity of the heart. So now you're talking about not just measurements of heart rate or heart rate variability, but the full electrical waveform associated with each cardiac cycle. And you're doing that not in an episodic way, which is possible with the Apple Watch, but continuously. So you get every heartbeat, not just a heartbeat when you activate the measurement. And that can be done continuously for long periods of time. And, again, the consequence is you end up with vast amounts of data, but new tools in machine learning can handle that kind of data and extract meaning. So you can see the PQRST waveform. Cardiologists know what to do with that type of data. The other kinds of measurements, many sorts of measurements require this physical contact with the skin. And I just illustrate a couple of others here. Hydration measurements of the skin. You want to measure how the hydration status of an individual or of their skin, various kinds of skin disorders associated with low hydration. You can do that as well, either electrically or thermally. You can measure precisely the amount of water content in the skin. Again, requires physical contact, but with these kinds of skin-like devices, it's easy to establish that contact and maintain it over long periods of time. Another example, in addition to electrical, thermal, you can measure mechanical characteristics of underlying processes. So, for example, pulsatile blood flow through near surface arteries. You can pick that up with pressure sensors integrated in these devices. So you can measure hemodynamics and essentially do arterial tonometry. But again, not just when a patient presents themselves at a hospital and you're in a clinical environment, but now continuously, in the home and during natural daily activities, you can do that as well. So anyway, there's a whole zoology of devices that are now available for measurements of those types, but far beyond those as well, to include really dozens of different relevant parameters. And you can do this in a purely wireless fashion as well. So again, continuous capture of data, and you're not restricted just to the wrist. You can put the devices wherever they're needed, depending on the patient condition and the measurement and the measured quantities that one is interested in. And so this was a National Geographic piece that was highlighting our work in this area in 2019. So by now, this is a sort of a global research effort. I mean, we're just one group of many working in this area of skin interfaced biosensors. And I would say there's probably hundreds of papers that have been published at this point around all sorts of different types of sensors that you can integrate into these skin-like platforms based on thermal effects, electrical. I'll come back to fluidic in a little bit, mechanical, optical, even acoustic sorts of measurement capabilities are now available. In each one of these devices, you can imagine integrating multiple sensor types. So each device can operate in a multimodal fashion, but you can also mount multiple devices at different locations across the body of an individual patient, and you can run those devices in time synchronized fashion. So each device is not only multimodal, but they can be operated in a multinodal fashion. So again, tremendous amounts of data. Clinical quality data is what we aim to achieve with the sensors that we're developing. continuous and wireless, and ultimately, with cost structures that will allow availability across all areas of the globe to everyone. And that's an important part of what we aspire to achieve here as well. And I'll describe some examples of deployments into Africa in a few minutes, just to illustrate some of our activities along those lines. So, where do you start? You have a technology like this, you want to have impact on patient outcomes. What patient population do you start with, in terms of a focused effort? And we decided that premature babies might be a good place to begin because these are classes of patients that are in extremely fragile health status, and conventional monitoring technologies are poorly suited to these patients, as illustrated on the left, which is standard of care in a hospital in the U.S. So you need to monitor all of the vital signs 24/7 associated with these patients, and that's done with wired-based biosensors that connect on one side to boxes of data acquisition electronics. On the other side, the interface exists in the form of a taped-on sensor interface to the skin. And there's all kinds of problems with this approach to caring for these patients. There's a mechanical constraint. The babies can't move around very effectively. It's difficult for parents to engage with their child. And the tapes themselves can cause skin injuries, because the skin of these patients can be very fragile, and these sensors need to be applied and removed on a 24-hour cycle typically. And so the vision and the idea in this slide was created some years ago was for us and as a group to take some of these ideas in skin like wireless electronics and build into them all of the kind of measurement functionality that's currently supported by these wired approaches to improve how these patients are cared for. So this is just a Photoshop illustration of what we had hoped to achieve. I think I made this slide maybe in 2015. But it turns out that you can do all of that. And again, this is not a hardware, not a physics or material science talk, so I won't go into details. I just want to highlight what kind of data is coming out from these kinds of devices. So this is just a picture of the outcome of about 3.5 years of focused work on devices to address patient requirements in that context, premature babies. So it's 2 devices, one that interfaces with the chest. That's what you're seeing resting on the fingers in this picture. And then one that goes on a limb, either the hand or the foot. That limb unit measures blood oxygenation optically, as you can see from those LEDs that are activated in the device that's resting on the palm of the hand. The device that's going on the chest is measuring cardiopulmonary activity. So it's capturing ECG, heart rate variability, respiration rate, and there's also a temperature sensor embedded. And these devices are operating in a battery-free mode, so we're doing wireless power transfer to support their operation. And then that same magnetic inductive wireless link establishes a path for data communication. So it's continuous wireless operation, both from the standpoint of power supply and data communication as well. So this is what it looks like on a premature baby at our Lurie Children's Hospital here in Chicago. You can see the device on the chest, as I mentioned, doing cardiac measurements, respiratory rate, and you can see the wired devices being used simultaneously. So we have one-to-one comparisons of data streams captured with our devices against those captured with clinical gold standards. So that's what it looks like. We've done probably about 200 premature babies at this point, no adverse events. We have tremendous amount of data to validate the operation of these devices, their safe operation, and their accurate clinical grade operation. So you don't lose anything in terms of clinical accuracy. In fact, I think that the data quality is a bit better because you don't have motion artifacts that can be induced by the wired interfaces associated with conventional monitoring systems. So that's what it looks like in the NICU. That's a neonatal intensive care unit. We've migrated and expanded into the PICU, the pediatric intensive care unit. These are bigger babies, but they still require, in many cases, continuous vital signs monitoring. And this is an example of the baby with its mother, and you see the device on the chest there, highlighted pretty clearly, and the one on the foot that's doing blood oxygenation optically. So the antenna that's doing wireless power transfer and wireless data communication is mounted in the base of the chair in this particular case. And so eliminating the bulk and the size of the battery really allows us to build these systems in that skin-like format, thus our terminology of epidermal electronics to refer to these technologies. And just kind of highlight that skin-like characteristic. This is a device that's been mounted on the baby's back. Turns out you can measure cardiac activity from either the chest or the back. And you can see as the baby rotates around to look at the cameraman in this case, the skin of the back wrinkles in a natural way, and the device wrinkles right along with the skin. So there's very little mechanical load, very little mechanical constraint associated with natural movements of the skin imposed by the device itself. And the other consequence of that is that you don't need a very strong adhesive interface to keep these devices mounted on the skin. They're very skin-like, and so the interface stresses associated with motions of the skin provide only a very small driving force for delamination. So even a mild adhesive is good enough. And of course, you don't have a wire tugging on the devices, which is also important. So we can use an adhesive that has an adhesive strength about 10 times lower than that associated with the adhesive tapes that are used to keep the traditional wired biosensors adhered to the skin. So that's what it looks like. So we published those results in spring of 2019. Shortly after, we were contacted by program managers at the Bill and Melinda Gates Foundation and also from the Save the Children organization to think about whether we could deploy those devices into lower and middle income countries, and where there in many cases aren't monitoring technologies available at all, wired or otherwise. And so we're in the middle of a 10,000 unit deployment starting in Zambia, Kenya, and Ghana, but we'll be extending into India and Pakistan as well through the end of this year. And that's turned out very nicely. It really required kind of a re-engineering of many aspects of the devices I just talked to you about to increase their mechanical ruggedness, to allow their multiple cycles of reuse, and also to enable operation without requirements for a stable wall plug source of power that would otherwise be needed to operate the antennas that I described for wireless power transfer and data communication. So we actually made a number of changes. We also modified the engineering so that the manufacturing processes are well aligned with the kinds of capacity that currently supports the consumer electronics gadgetry industry. So we're able to do all of that. And we published the results last spring 2020, in Nature Medicine, and it's highlighted on the cover of that March issue. And so back to the data. What do the data actually look like? Well, here are some examples from those latest sort of deployable devices that we reported spring of 2020. So it's ECG. We talked about that already. The blue curve in the top graph. It's PPG, photoplethysmography, and so we're getting time series data associated with optical reflectance at two different wavelengths, one in the IR, one in the red. You can use those data to determine blood oxygenation, but there's actually a lot of additional information content associated with the actual waveform shapes, and so we have those two time series data streams as well. In these devices, we've also included essentially microphone. It's actually accelerometer, but we can measure heart sounds. We can measure sounds associated with opening and closing of the valves. So those sounds give you, simple things like heart rate variability, but it's actually additional complementary information that's not embedded in the electrical waveforms associated with electrocardiograms. So this is additional data stream that is not even captured in the most sophisticated NICU units here in the US. So this is going beyond the standard of care to something better and more insightful in terms of data quality and data breadth, I guess. It's also accelerometer, so we can measure cycles of motion of the chest wall cavity, so we can detect respiration in that fashion. And so the simplest way to take these data, these raw data streams, is just process them very simply with digital filtering algorithms to determine heart rate, to determine SpO2, blood oxygenation, determine respiration rate, temperature, this sort of thing. That's the most basic approach for data analysis. And I think it's really only skimming the surface of the actual information content that's present in the recorded data. And so that's where I think machine learning and artificial intelligence can come in. There's like extract deeper insights from the ECG, not just the heart rate. Really look at that waveform shape and think about sounds as well. So that's the the device platform. We're deployed in 23 countries at this point through the Gates Foundation and Save the Children Foundation support. But we also have partnerships with Draeger and BARDA and Anthem and others as well through a startup company that's kind of an outgrowth of my academic group here at Northwestern. So again, thinking about advanced metrics, so I mentioned cardiac sound, some other things, thinking about the NICU of the future and additional data streams. Now you have a validated wireless platform. What other kinds of sensors can you embed in that system, and what kind of information and insights could one obtain from those additional data streams? So for example, we can track body orientation of the baby with this high bandwidth accelerometer mounted on the chest. And so we can get deep insights into what's going on with the baby and how restless they are, for example. What is the activity level? We can determine when they're, in their mother's arms and when they're in the isolate, for example. We can also, as I mentioned before, we're getting cardiac sounds. We actually get sounds of vocalization as well. So we can determine crying time and tonality and patterns of crying and when crying is happening and how those crying episodes are correlated to cardiac activity and so on. So tremendous depth of information. And we're just beginning to think about all the different measurements that could be made and really beginning to ask questions around what kind of data analytics do we need to add to this hardware to really improve the value that is bringing to clinical care and to patient outcomes. So these are some other things that we're just now beginning to think about and to look into. The other thing, and I mentioned this previously, is that the devices are time synchronized. And so we can measure when a cardiac cycle generates a pulse of blood from the measurements captured with the chest unit, but then we can also measure when that pulse of blood arrives at the hand or the foot through measurements with that limb unit. And they're time synchronized. So we can determine hemodynamics, so how quickly is blood flowing through the vasculature. And it turns out that in adults, that characteristic velocity, pulse wave velocity, can be correlated to blood pressure. So now you can think about hemodynamic measurement of blood pressure on a beat-to-beat fashion in a way that doesn't require an arterial line or a blood pressure cuff, both of which are very difficult to use with small infants for obvious reasons. And so we're just beginning to publish papers now on blood pressure measurements by the combined use of time synchronized data coming from a pair of devices. So again, multinodal, multimodal, these are some of the concepts. So it's not just the data streams off of one particular device, but it's correlations between data streams that are being collected from multiple devices. Again, huge opportunities for advanced data analytics around those kinds of databases. So, we have these devices are kind of entering the translational pipeline. We just got FDA approval a couple of months ago, and it's one of many devices that we're pushing in this direction, with a focus primarily on neonatal and pediatric health, but also with an expanded focus lately on maternal and fetal health as well, because a lot of maternal death happens during childbirth. And could we measure maternal health and fetal health to improve outcomes for mothers during delivery and also improve outcomes for the neonates immediately after delivery? And so that's an area that I'll say a couple of words about. So now we're using 3 devices, all time synchronized, to measure health of the fetus and health of the mother. And so we have a chest unit, a limb unit for the mother. We have an abdominal unit to capture cardiac activity of the fetus. We're also capturing uterine contractions and the orientation and positionality of the mother during delivery. So this is published just a few months ago, and these are the kinds of data streams you can capture. So we can see fetal ECG, we can measure cardiac sounds, both of the fetus and the mother simultaneously, and it all correlates quantitatively with the kind of hospital apparatus that's used today, wired systems that are costly and far inferior actually to the kinds of wireless devices that I showed you in the previous slide. And so through the Save the Children Foundation, we have deployed these devices at scale into Zambia. And so we published just a couple of months ago results of measurements of 487 women in Zambia during delivery, the entire delivery process. And so as they present themselves to the hospital, they're outfitted with these sensors, and then measurements are made continuously until the delivery has been completed. And so now we're beginning to be able to capture kind of population scale data sets. And the idea here is, you can think about the health of an individual, but now you have statistically relevant information on health trajectories as mothers, deliver babies in general. And so again, data analytics is going to be very powerful here, not just looking at single time series data, but looking at such data collected from large collections of individuals to look for trends and patterns and things that machine learning will be able to pick up that maybe doctors and nurses have overlooked. I think this is an exciting frontier, and we're just getting started. We haven't really analyzed these data sets in the kind of sophisticated ways that I think are possible, because that's not our area of expertise, but we do have the data at this point, and we have sensors that can collect this kind of data with very, very high accuracy and high effectiveness with deployability around the globe is the idea. So hopefully that gives you a sense of maternal, fetal, neonatal, pediatric health. At the other end of the age spectrum, there are also different sorts of health challenges. So thinking about elderly care and the kinds of disorders and health challenges that those types of individuals are exposed to and have to struggle with. And so let me say a couple of words about what we're doing with stroke survivors, Parkinson's patients, Alzheimer's patients, specifically around aphasia and dysphagia. So these are conditions that sometimes will follow a stroke, also a consequence of Alzheimer's and other neurological disorders that involve an inability to speak and swallow in a natural way. And so these patients will come into a rehabilitation clinic, and they will be instructed and trained on how to speak properly and how to swallow at the appropriate time and with the appropriate frequency. And this is a picture of a patient at our rehabilitation hospital clinic here in Chicago called the Shirley Ryan Ability Lab. And the rehabilitation specialist approached us and described a situation in which patients who present to a rehab clinic come in, and the rehab specialist can see noted improvements of swallowing and speech behavior while the patients are in the clinical setting, but when they return to home, a lot of those gains dissipate. And so the request was for a sensor that would allow them to track patterns of speech and patterns of swallowing during the natural activities of the day outside of a clinical environment, in a home environment. And so we are able to develop a device that mounts on a unique part of the anatomy known as a suprasternal notch to measure motion characteristics over a wide bandwidth. So subtle vibrations of the skin, also movements associated with swallowing, and with the capacity to capture those kinds of data streams continuously over long periods of time, so that they can be analyzed and examined and used to sort of personalize a rehabilitation approach to an individual's condition. And so these devices mount on the base of the throat, and you can capture vibratory signatures of speech. You can measure motions associated with swallowing. You're also close enough to the carotid artery. You can pick up signatures of cardiac activity, so you can get heart rate and heart rate variability. You're coupled to the top of the chest wall cavity, so you can get motions associated with respiratory cycles, but also respiratory sounds, coughing, sneezing, wheezing, this kind of thing, body orientation, motion, steps, and so on. So It's a very powerful location on the body for collecting health-related data, and it's really a position that's completely outside of the scope of a traditional wearable. It's really hard to imagine how you could mount an Apple Watch on the base of your neck, for example, or Fitbit. But with this soft, skin-compatible electronics, it's very easy to do that. It's almost like a Band-Aid. You just place it wherever you want it. And in this context, for this set of patients and these applications, the suprasternal notch is a great position for that. So the simplest thing you can do is you can monitor patterns of speech, but you're doing it in a way that's immune to sound, because this is not a microphone. This is a device that's measuring vibrations of the skin. And so you can capture individual speech patterns even when they're having a conversation with someone else without the confounding effects of the speech of that associated with that other person. So it turns out to be a very easy way to collect patterns of speech at an individual level. You can also, at the same time, as I mentioned before, capture cardiac activity and swallowing. So here's an example of raw data, the top graph, captured from a patient while they're sitting still and they're not speaking. And what you can see is it looks kind of like noisy data, but if you apply digital filtering algorithms, you can separate out the high frequency components, and that's what you're seeing in that middle graph. Those are cardiac sounds, and so you can measure heart rate variability very easily. You get that immediately. You subtract out that high frequency component, and then you're left with the respiratory cycles. You can see these oscillations up and down. That's corresponding to inhalation, exhalation. But then you also see these sharp events periodically riding on top of those respiratory isolations. Those are swallows. You can determine when an individual is swallowing, and also when they're swallowing relative to the respiratory cycle. And it turns out that's very important information as well, because if you swallow at the wrong point in a respiratory cycle, you can choke yourself in ways that can be very dangerous. So these are the kinds of data streams that emerge, and they're all separable. So you have a single time series data stream, but each one of these activities has a unique spectrogram associated with it. It has a unique temporal and spectral set of characteristics. And so you can see cardiac activity looks much different than talking, much different than swallowing, steps, and so on. So the easiest way to do the data analytics then is to simply apply digital filter algorithms to basically separate all these different activities, classify them, and then bin them. So you can determine cardiac, but you're also determining respiratory and swallowing and motion and all these other activities, and that works pretty well. And we've described the details of those approaches. So not really requiring machine learning, but as you begin to look at subtleties, let's say the difference between speaking and coughing, that's where convolutional neural networks turn out to be very, very powerful. And so let me talk a little bit about that. So we were engaged with these stroke survivors, deployed at scale through early 2020, and then the pandemic hit, and we began to get quite a bit of inbound requests around the use of our device to track symptoms associated with COVID. And the top 3 symptoms are fever, cough, and shortness of breath. And you can't get any of those parameters very effectively with a traditional wearable because you're not coupled to the respiratory system. You can't even get an accurate temperature measurement from the wrist. But our devices, can measure these quantities directly, from the suprasternal notch. What we needed to do, though, however, is to scale up production of the devices and also develop machine learning approaches that can capture coughing events separate from speech. And that's what we were able to do. And I won't get into the details. We had, half of the whole team was really focused on this, and we were able to start deploying in April of 2020. At this point, we have 100,000 hours of data, 60 weeks of deployment, more than 500 subjects, and tremendous amounts of data coming back to data analytics. There's just tremendous richness in the data, tremendous volumes of data. And the recordings happen continuously up to 36 hours. The devices are recording onto a memory module embedded in the device, and then we upload the data to the cloud server where we apply data analytics to yield, essential parameters that can be tracked by physician or nurse through a graphical dashboard interface on the web. And so we produce devices in our labs, hundreds of devices in this way. It's quite a heavy lift, and then distributed them to hospitals across the Chicago area at the scale I mentioned before. And we can track patients. We can also track frontline healthcare workers, and we can do this over long periods of time. So we can either pick up very early warning signs of symptoms of COVID and maybe triage then the use of molecular tests, and that's what was done early in the pandemic. But we can also track the status of patients who've already contracted COVID-19. So we can look at whether their conditions are improving or deteriorating. We're doing that in the hospital and in the home. So you can release a patient to the home with a device, and then the physicians can track them remotely. And if they undergo a period of deterioration, they can be brought back to the hospital as necessary. So tremendous amounts of data here, coughing events for a particular patient, multi-day data in the hospital, heart rate, respiration rate, physical activity, and so on. This is an example of a patient who was in the hospital and then released back to the home, and you can see cough count as an important indicator of health status and how that evolves as the patient recovers. So these are some of the types of things that are possible. We just published the initial results of some of these studies a few months ago, and you can take a look at that, and all of the details around the machine learning algorithms that we developed for cough identification are described in that paper. But again, we're not experts in machine learning, and I think the community, that I'm addressing now, could do things at a much higher level of sophistication. But this is what we were able to put together ourselves on a short timeline. So the other interesting thing about cough is it also provides an indirect measurement of how infectious a patient is, because coughing is producing aerosols, and the intensity and frequency of coughing is determining the total volume of aerosols that are being produced. And so we've done a lot of high-speed video imaging of aerosol production in this way, and we've been able to correlate the volume of these aerosol particles to the measurements made with this device mounted on the suprasternal notch, which is capturing not only coughing events, but also the intensity and duration of those coughing events as well. And so where we're going with this now is using these devices to try to assess and determine whether someone is sick or not to simply track their status as they recover. And one of the aspects of COVID-19 is extreme high levels of fatigability. And so we have the ability to now look at how heart rate changes following a period of activity. And initial studies, we were asking patients to walk around the room at certain time points, and we could measure heart rate before and after. But then we realized we don't even need to ask them to engage in that specific set of activities. We can just track them during their natural daily activities to determine what kind of changes in heart rate are associated with different levels of physical activity as a way to determine that. And so we've done some principal component analysis that seem to indicate that this does, in fact, represent a very powerful and effective way to make an assessment of whether someone is becoming ill or not. Not whether they have COVID or the flu. That level of specificity is probably outside of the scope, but at least some kind of continuous ability to measure whether someone is becoming sick or not. And so this is ongoing work with Dr. Arun Jaramayan at Shirley Ryan Ability Lab. So I think I'm pretty much out of time, and so I'm going to just skip through the sweat analytics work. I mentioned at the outset of the talk that we have not only electronic devices, but also microfluidic platforms that are skin compatible, and we can capture sweat. And sweat is an interesting class of biofluid because there's tremendous amount of biochemical information content, but it's a class of biofluid that can be captured non-invasively. And so that's really driving our interest in sweat as opposed to blood or interstitial fluid. And so we have color changing chemistries that allow us to determine biochemical markers in sweat concentrations, and we can do that in situ. And it turns out to be a powerful way to determine nutritional balance, electrolyte balance, for example, to determine whether someone's been exposed to heavy metals, for example, in the environment, and so on. And so there are many things that you can do here. And I guess maybe what I'll say, because I'm almost out of time, is I think the future is combining electronics with microfluidics. So now you're able to capture not only biophysical signatures of health status, but also biochemical markers that provide additional complementary types of insights. So coming back to the idea of data science, you have this tremendous information in biophysical data streams. Now add to it biochemical information. I think that will be very helpful in improving assessments of health and care of patients ultimately. So I think I'm going to go ahead and conclude. So I was able to say a lot about these epidermal electronic devices, different capabilities, different kinds of patient populations that we've looked at. Unfortunately, I didn't have too much time to talk about the microfluidics, but hopefully enough time to give you an idea of the complementary capabilities that are provided by epidermal microfluidic devices. You can combine the two, obviously, as I just mentioned, and I think that's going to establish a very versatile platform for the future. So I'm going to go ahead and conclude and do so by acknowledging senior collaborators across various areas of engineering science, but also clinical medicine and sports. That the interfaces that we have to those communities are very much essential to the work that we do. But the most important people are the students and the postdocs who are actually doing the work. I'm just talking about it. And so this is a picture of the group that we took shortly before the pandemic. It looks more or less the same in terms of the size and the scope, but really talented individuals, and it's a real honor and pleasure to be able to work closely with these folks on topics of this sort. So I'm going to go ahead and conclude. I'll be happy to answer questions if there are any. I'll go ahead and stop sharing my screen here, and I'd be happy to answer questions if you haven't.
Thank you very much, Professor Rogers, for that fascinating talk and where the technology, the state of art is right now. There are many questions here. I'll just first ask a couple of questions that I'm curious about, and one thing that my colleagues might be very interested in is most of this data available publicly so that they can look at it or analyze, as you mentioned?
Yeah, it's available through our publication. So I think that PNAS, for example, has a mechanism by which we can share these data. I think if individual people have specific interests, perhaps they could send me an email directly, and I could have start a dialogue and provide the data with appropriate labeling.
Yeah, absolutely. Great. Thank you. Yeah, so they should just write to you, and that can.
Yeah.
On to panelists and the audience questions.
Can I ask
my own interest in spinal cord injury actually leads to this question. So one of the major problems with spinal cord injury patients is bladder and bowel control. I know you work on the skin, not inside the body, and there's a tremendous amount of efforts going on to actually sense the bladder pressure and then maybe stimulate a nerve or inhibit a nerve depending upon what needs to be done, so that you can have ease the discomfort of the patient and have some semblance of control. So do you see the similar kind of devices that you are making? They can actually be put in vivo and used for something like that?
Absolutely. We published a number of papers on devices that interface with the outer surface of the bladder so we can measure filling and voiding events. So far, just in animal model studies, but we can monitor bladder activity. We also use optogenetic approaches to stimulate or inhibit voiding events, and we can do that in a closed loop fashion. We published a paper in Nature in 2019. You could take a look at that if you're interested. I mean, I think it's maybe a future sort of engineering approach to treat overactive bladder. That was the focus of that paper, and we work closely with experts at Washington University's medical school. We also have an existing NIH-funded program on bladder reconstruction and monitoring bladder activity following a surgery that addresses a reconstructive effort associated with with the bladder. We do have a new effort on measuring bladder pressure. So these are devices, they're going inside the bladder. We have not published those results, but I'm very optimistic that we can build that technology and make it work reliably. But I would say it's still maybe the early phases of that program of work. But it's an area that's a very high interest to us. We're also developing sensors for measuring solid material movement through the gastrointestinal system, specifically the colon. Again, mainly in the context of animal model studies to get to answer basic biological questions around GI activity, and that's in a collaboration with a physician in Australia. So we have soft strain gauges similar to the ones that we developed for the bladder that interface with the colon, so we can monitor continuously and in a wireless fashion GI activity in that way. So two topics maybe that are related to your interests, as it pertains to spinal cord injury. So those are definitely areas where these same concepts in soft electronics apply very nicely. So we're not just working on the skin. We have brain interface devices, cardiac, I mentioned, spinal cord, and others. Yeah.
Thank you. Yeah, it's just nice to see there is some India Connect there where your devices will be tested here pretty soon. And I'll request one by one some panelists to ask questions. In between, I'll take some audience questions. So, Professor Vadera, do you have any questions for Professor Raj?
First of all, I think it was an excellent talk and a really wonderful topic. I was just having, are these things now commercial or we are in the process of commercializing?
Yeah, so we have a startup company that is producing these devices at the scale of several thousands, and they're engaged with the Gates Foundation and the Save the Children organization in the programs that I mentioned. They just recently received FDA approval, so that was kind of a prerequisite for any kind of real commercial deployment beyond the Gates pilot studies. So it's headed in that direction, I guess, to answer your question. I think it's likely that they'll be broadly available next year, this coming year, for non-critical care applications. So the FDA approval process, it's different, if you're doing ICU monitoring as opposed to just remote patient monitoring. And those deployments will likely be happening through Anthem, which is a large medical insurance company here in the US, and they're interested in monitoring the health of their customers in a home environment. It's likely not going to be a consumer-oriented device. It's more of a approved device that will be deployed on a prescription basis or through a partner like Anthem.
Okay. How cost effective or what way, cost of these devices are going to be if it is to be used by general hospitals kind of things, or how it is going to be, or how much time it may take to reach to those levels, perhaps another way of
cost is a really important consideration. I think if the Gates Foundation wasn't convinced that we could build these devices and use them in a cost-effective manner in Africa, they wouldn't have funded the program. So we went through with them a costing exercise to sort of project what the costs might be once manufacturing is at a high volume level. So it's a lot of projections, obviously, but there is a case that can be made that you can realize costs as measured in the cost of a patient monitoring day. So on a single patient, monitor them all day. What is the cost associated with that? Of something in the range of cents, so 5-7 cents, something like that. And the way you get there is you build the devices so that they're rechargeable and reusable, and you can amortize out the cost of the device itself if you use it over a sufficiently large number of cycles. And so then the cost is dominated by the consumable component, which is the adhesive that bonds the device to the skin. That's not reusable. Everything else is reusable. So that's the kind of cost model that we put together and the mode of use. So it relies critically on reusability. If you don't have reusability, you can't get anywhere near a cost number that would be relevant for anything other than, let's say, hospitals in the U.S. You could do it because everything that's used in the NICU is disposable. So they're throwing away even NIR systems, which are $100 monitoring devices. They only use them once. But that turns out to be a small component of the overall cost of maintaining a baby in a NICU facility. So they do things that way, but you can't do that in Zambia or Kenya, Ghana, other places. So you have to think about things in a different way. But reusability and costing out on a per patient day basis is the way you think about it.
Of course, I have many questions, but last question I would be going on to. Anything in the area of imaging through wearability?
Yeah, so imaging, I guess I could say a few words about imaging. So there are groups who are looking to develop, ultrasound imaging capabilities in devices of this general sort, so skin interface devices. There's a prominent group, it's former postdoc out of my group at University of California, San Diego, has made good progress in that direction. Another former PhD student at MIT Media Lab is also working in that direction. We are not, I'm interested in it, but I don't want to compete with my former students, so we haven't gotten in that area. But I guess in terms of imaging, there are those efforts, that are ongoing around using ultrasound. You might be able to use optical approaches for imaging, arrays of light emitters and detectors. We're doing a little bit of that in the context of monitoring activity in the brain. And so that's an area of opportunity, I would say. But the other way to answer your questions, are these devices compatible with existing standard imaging modalities, X-ray, CT, MRI, and so on. And in the paper that we published in Science in 2019, we looked at those issues very carefully. So if the device is operated in such a way that there are no electrical resonances at the operating frequencies of the MRI machine, they're essentially transparent to MRI, and so they're MRI compatible. And we demonstrated that in animal model studies. And then in terms of X-ray and CT imaging, I would say that the shadowing is minimal because the overall area coverage of X-ray opaque materials is small, and it has to be small because we want soft mechanics. So the areal density of the electronics and the interconnects are fairly small, so you can image right through them. They're transparent at that level, so they're compatible with CT and MRI, and that's an important consideration in a lot of contexts, because these patients need to be imaged on a regular basis, and if you don't have to take the device off in order to do that imaging, it's very useful clinically. So.
Yeah, thank you very much. Excellent talk. Compliments.
Thank you. Yeah.
Thank you, Professor Raj. I can see you have already answered one of the audience questions from Shilpa, that are these devices reusable. I'll ask Professor Ajay, do you have any questions?
Neeraj, I have a question. So,
Yeah. So
yeah, just 1 minute. We'll go one by one.
yeah.
Yeah, Professor Ajay, yeah, go ahead.
So excellent talk. Again, I'll compliment an excellent work by Professor Roja. I have a couple of questions, small questions. One thing you mentioned, these patches can be removed and can be reused. So how easy it is to remove, because there is a glue layer all over, and if there is a glue layer all over, how these are used for microfluidic application?
Yeah, great question. So we're using dual-sided adhesives that bond on one side of the device and then the skin on the other side. And we've decided to stick with adhesives that are already well developed and FDA approved for use in skin bandages. So you almost think of this device as a bandage, and you're just putting it on the skin. So it goes on just like a Band-Aid, I guess, in a sense. I mean, you have a peel-off dual-sided adhesive. You expose the adhesive side, you just stick it on. That's it. And then when you take it off, you just peel it off. So that's what's going on. I guess there are risks for skin injuries if the adhesive is too strong for elderly patients, for very young patients, infants as well. But we've sort of balanced those considerations. I mentioned, that there is a reduced need for a strong adhesive when you have a soft, thin, lightweight device, which makes intuitive sense. So different ways to address that problem, either from the standpoint of the adhesive or the device design. So that works. As I mentioned a few minutes ago, we don't attempt to reuse the adhesive. So the adhesive is the only thing that's really contacting the skin. The device is separated, and then the adhesive is disposed of each cycle of removal and application. So that's kind of the glue. It's not a liquid glue. It's a thin film, that's just adhesive on both sides. Yeah. So, and there was a second part to your question.
Yeah. So because if there is a glue film in between, how that sweat is going to the device for the microfluidic application? Is it not hampered because of this film in between?
Yeah. So the adhesive has holes cut in it, and so the back side of the microfluidic device has little inlet ports. The microfluidic channels and reservoirs are totally sealed, and you only have a well-defined opening to the skin.
Okay.
And that opening inlet is aligned with a hole that's cut in the adhesive. So the adhesive is hearing everywhere except at that region where the sweat is allowed to emerge and then enter into the device. So the sweat glands themselves are pumping the fluid up through that inlet port, through the hole in the adhesive, and then into the microfluidic network. But I think that your broader question maybe is like, how do you deal with sweat, and does sweat disrupt the adhesive strength? And it can. So in some cases, we cut channels into the adhesive, or we add a fabric layer that can whip the sweat away from the interface between the device and the skin to the perimeter where it can evaporate. So you have to think of, these are great details. It's because it's not just sweat. Your skin is constantly allowing water to permeate through. So there's natural transepidermal water loss, not even sweat, and that can also accumulate at the interface. And if you get too much moisture buildup at the interface between the device and the skin, it can compromise the adhesive strength, as you're suggesting, but it can also create redness and rashes and adverse skin reactions. So you need to manage that accumulated moisture, and the way that we do it, I just mentioned, either the fabric or the channels that we cut into the adhesive to allow for outlet of that moisture.
So also the sweating pattern under the patch and outside the actual sweating have you done any study on that? Because if it is covered, the skin is covered by a patch, the sweating pattern or the components of the sweat may change also.
Yeah, that's very important. So you're asking great questions. So these are issues that we've looked at very carefully. So it's called compensatory sweating. So if you have an adhesive, let's say, that's blocking a large region of the skin, except for a small region in the middle, the sweat rate coming out of that region will be greatly enhanced by the fact that you're blocking sweat in all adjacent regions. But there's a length scale associated with that. So if you're blocking sweat from some distance greater than some minimal distance away from the region you're collecting sweat, it will have no effect on the rate at that position, as you might imagine. So when I say we cut channels, we do it partly to allow release of accumulated sweat, but also to minimize that compensatory sweating effect. And we study all these things in very great detail, and we publish them, because because that acceleration could be like 5, 6, 7 times. I mean, it could be huge enhancement of sweat rate. And so then the sweat rate is artificially increased, and it can change the relative biomarker concentrations. And if you're trying to get a sweat rate you've introduced a massive artifact, and you really have to pay attention to that. Very, very good question.
Yeah, thank you very much, and I'd like to understand more on that aspect, so that so is it any possibility of working together in that particular area? And I think you can
Yeah,
explain something.
I think it's really interesting. I mean, we basically design our devices to avoid that effect. We're not trying to exploit it or engineer it. We just don't want it to be affecting anything about our sweat rate measurement. But I guess there would be ways, maybe you could exploit it or take advantage of it somehow. Maybe that would be interesting. That has not been our focus up to this point. Just try to figure out how to engineer that effect
Sure.
out of the measurement.
Okay, thank you.
Yeah.
Thank you very much.
Okay, thank you. Before I return to the panelists, I just have a question from the audience, very interesting question from the Panjan. So you are measuring mechanoacoustic aspect. Now, can that be used for autism diagnostics in children or adolescents?
No, for sure about that. I mean, that's a great question. We're doing vocal biomarkers, as I mentioned, coughing, wheezing, that kind of thing. We have a deployment on pediatric patients with cystic fibrosis, and symptom of that is coughing, kind of a wet cough, and we're sort of classifying different types of coughs as dry cough or wet cough, or is it a heaving cough? There's all kinds of labels that you can put on coughs, and then use machine learning to sort of classify the measurement according to those different types of coughs. And like I said, we're working with kids who have CF and monitoring their coughing characteristics in the home. The other thing that we're doing is we're attempting to measure just the sounds of respiration. So we've been measuring respiration rate through cyclical measurements or cyclical motions of the chest wall cavity. That can be a relevant measurement of respiration, but in some cases your chest wall cavity can move, but you actually haven't, that hasn't resulted in airflow. And so you'd like to be able to measure the sounds of airflow themselves to be able to characterize that. So that's a little bit more subtle. It turns out to be right on the hairy edge of what we can do in terms of the sensitivity of our device. So it's something that we're working on from the standpoint of enhancing the engineering features to allow that kind of measurement. But I don't know. Autism sounds really interesting. It hasn't been something that we focused on or thought about. I don't know if there's additional detail or ideas you have about how a mechanoacoustic measurement could be relevant as a way to diagnose autism. Hello?
Yeah, I actually lost the signal momentarily at my end, so that's why I disappeared. I turned off my video also. So yeah, because autism sometimes with the speech pattern itself has signals of autism, and I think that's where the question is coming. So
yeah. No, we haven't looked at that. No, that's a great suggestion.
Yeah. Professor Mitali?
Yeah. Professor Rogers, first of all, a very fantastic lecture. I work in the area of precision medicine, and for some years we've been actually using skin also as a kind of a window for looking at physiological differences in adult humans for stratifying adult individuals. And we had used these instruments, but they require a lot of conditioning before of an individual before we can take measurements, because its skin is inherently very, very prone to fluctuations of the weather conditions or temperature. I just wanted to ask whether how do you visualize whether these kinds of instruments could be used as a in kind of precision health studies in outside field settings? How useful or how accurate it would be, or would it not be so well yielding, given that skin is so much prone to uh, fluctuations, even a small stress or temperature or weather can do it. And the second thing is, have you also tried using it for stratifying healthy individuals in any time? And would you actually have some data we can look at?
Yeah, those are good questions. So I guess it depends on the type of measurement that you're making, whether you'll be sensitive to the detailed properties of the skin itself or not. So I think measuring vocalization or swallowing, like the detailed properties of the skin probably don't matter too much. It's just transducing a mechanical movement or a vibrational signature of an activity like speech. So that's, or cardiac sounds would be the same thing, I would say. Even for electrocardiogram measurements, you know, the impedance of the skin can vary depending on the hydration level, for example, or contamination on the surface of the skin. But for ECGs, you're typically not looking at the absolute amplitudes, but the relative amplitudes of different features within the ECG waveform, as I'm sure that you know. I would say similarly with PPG, also it's optical measurement. So maybe the optical properties of the skin could be different depending on pigmentation or sun exposure, for example. But there again, you're looking at the ratio. You're looking at two different wavelengths, and you can subtract out some of these pigmentation variations. And there as well, a lot of the information is in the kind of the AC component. So you eliminate some of the effects. There are, as you are suggesting, however, types of measurements are very sensitive to the nature of the skin itself. And those measurements are typically those that focus on the skin as opposed to use of the skin to measure something underneath the skin. And so,
Yes.
for instance, and you probably know this, but we do a lot with skin hydration. I mentioned it very briefly, but we have major programs there because there are all sorts of dermatological conditions that relate to dry skin and compromised barrier characteristics of the skin. There, let's say you're measuring the hydration of the skin, very sensitive to how much pressure you're applying to the skin when you make the measurement of the hydration, because you're pushing free volume water in and out of the near surface. It's extremely sensitive, and it's a huge confound, and it makes it really difficult. You have to have some kind of at least basic training in how to use those devices. Otherwise, you introduce all sorts of artifacts by pressing the
Pushing.
device against the skin, or if the device resides on the skin for some period of time before the measurement, the hydration level can be dramatically changed just by accumulation of moisture from transepidermal water loss processes. So I would say of the various measurements that we've made and that we're looking into, skin hydration is the most sensitive to the details of the skin itself. But then, like I said, a lot of the measurements, it doesn't really matter too much. So it depends. You know, there are other kinds of we're measuring flow of cerebrospinal fluid through shunted hydrocephalus patients. There again, the skin properties don't matter too much because we're looking at asymmetries in temperature rather than absolute temperature changes. So the skin gets factored out, you know, in that kind of measurement. It's more of a relative measurement. So it's a good question. It's important in certain instances, but in most cases, it's not. The other question you had was whether you can stratify healthy individuals. I guess in principle we could. I guess most of our work is focused on individuals who aren't healthy. You know, so patients who have some kind of urgent need for monitoring. You know, the exception there would be what we did in the context of frontline healthcare workers and COVID-19. And so these are nominally healthy individuals. We were monitoring them with the idea of picking up an early sign of a symptom, like a slight increase in body temperature or an increase in the frequency of coughing, maybe a set of symptoms that the individual wasn't aware of. They didn't notice themselves, but now you have all the data. You can say, hey, you're coughing more today than you were yesterday. Are you okay? And you take a closer look. So there, I guess, would be an example of a healthy individual or a healthy population where we're monitoring and looking for emergent disease condition. But yeah, you can do that. Yeah.
Okay. Thank you. Thank you.
Okay, thank you. Dr. Totega, do you have any question?
No questions, sir. Thank you.
Yeah, thanks. I'll take one more question from the audience here. If you have checked how different vital signals picked up by different signals, that is sensors, I guess, synchronize with each other. So is there any individual variability in the synchronization?
Let me try to answer that question. I'm not sure I fully understand it, but I'll offer an answer. And if I haven't addressed your question, then let me know. So I think the question is, we have multiple redundant measurements of certain parameters. So the limb unit with the neonates is measuring heart rate. So is the chest unit, for instance. They're measuring the heart rate in totally different ways, but they're making that measurement. So typically we've set up algorithms that do cross checks. So if we're measuring a heart rate from the chest, it's much different from the limb unit, then we're alerted to that fact. And then we have algorithms that look at we have these signal quality indices. So if the limb unit has fallen off or there's some kind of artifact that's corrupting the limb unit data, we'll see that because the heart rate extracted from the limb unit is not consistent with that associated with the chest unit. Or another example is that we're measuring electrocardiograms, ECGs. We're also measuring cardiac sounds. Those are also two separate data streams that are yielding heart rate and heart rate variability, and we can check to see if there's an agreement between those two data streams. So the redundancy, I think, is very powerful, and you can take advantage of that. I think the other part of the question may have been something to do with time synchronization. So the way that we do that is we have a master device that's setting a clock, and it's sending its clock information to all the daughter devices once per second. And so all of the clocks are synchronized then one time every second. And so there's no long-term drift of clocks on different devices over a period of monitoring because it's being reset every second. So there's some battery consumption associated with that, but that's typically not an issue. And if you're doing that, you get time synchronization to within a precision of a couple of milliseconds, which is fine. I mean, in absolute sense, maybe that's not great synchronization, but it's pretty good, thinking about hemodynamics and delay times and such. About a millisecond is pretty good for most body processes, but that's limited by precision in the Bluetooth protocols and other approaches that we used for synchronization. And we've run up to 11 devices simultaneously. So we have one application where we're recapitulating full body motions for an automated data-driven assessment of neuromotor behaviors. So general motor assessments done, using data as opposed to trained neurologists. And so there we have 11 devices placed at different locations in the body, and they're all time synchronized. So with accelerometers and gyroscopes, we can reproduce body motions, again, to within that 1 millisecond, 1 to 2 millisecond timing accuracy. I think that hopefully that answered your question, but let me know if that's not the case.
Yeah, no, there's one follow-up question from the Panjan again. So now we're taking it a little bit different direction. He's talking about synchronization between the phase or amplitude of, for example, cardiac or respiratory time series signal or the EEG equivalent signal that you're obtaining. So is there any kind of synchronization that you observed in the data if you looked at it?
Yeah, EEG is tough. I mean, we have wireless devices for EEG in a clinical setting. I think home setting EEG, it's going to be difficult from a practical standpoint. The signals are very weak. They're very susceptible to artifacts. So we haven't looked at any kind of synchronized EEG, ECG behavior, for example. So I think that's maybe an important kind of interesting direction for the future, but we haven't done that.
Yeah. Thank you. Dr. Rajendra, you have any question?
No, sir, that is fine.
Yeah. Dr. Manish?
No, sir.
Okay. I'll just take one last question from Shilpa, and because it's getting late, and then we'll close it. You right in the beginning, you showed some tattoo-like devices. Now, are those real tattoos, or those are actually appeared like tattoo because they had a thin film like other adhesive devices? So Shilpa actually is asking, are they removable if they are
Yeah,
actually more like tattoo ink?
no, not ink. I guess it resembles a tattoo, but it's not. It's a device, and those features that you were seeing, those are components and elements of an active electronic system. So we like to, refer to them as tattoo-like in the sense that they're kind of intimately kind of integrated with the skin, but it's just an analogy. There's no ink associated with the devices, and there's nothing that remains on the skin. You peel a device off, and the entire system is decoupled from the skin.
Okay. Thank you, Professor Rogers. That is pretty early for you and a lot of discussion. And thank you for patiently taking all the questions. It's almost 2 hours actually. I'll just hand over for the closing. So can we go ahead? Yeah, I can't hear you actually. Dr. Totega, I can't hear you. I don't know if others can hear you.
No, we are not able to hear you.
Professor John?
Yeah, now we are able to
Yeah. Professor John, you see, I think it's a wonderful presentation, and it has a lot of applied values. And I will request Professor Zain that he should organize another lecture of Professor John. It was very interesting and a lot of good discussion we had. So on behalf of Jodhpur City Knowledge and Innovation Foundation, and also on behalf of Indian Institute of Science, Jodhpur, I am pleased to present a small gift for Professor John. I hope he will like this gift. Kindly accept it.
Thank you very much. Thank you for the invitation. It was a great discussion. I enjoyed the questions.
Thank you, Professor Rogers. We'll ship this over to your mailing address. I'll write to you about the mailing address so that we can just courier it to you. And thank you very much for this highly stimulating talk, which has actually raised a lot of questions and probably to an end of today's Thar talk, and hope I can persuade you to come again in
Okay, great.
few months'
Thank you
time.
again for the invitation.
Thanks.
Bye-bye.
Thanks. Okay. Have a good day. Yeah.
You too. Bye.
Thank you everyone for joining us. Bye bye.